Hello, welcome back. So in this part, we will discuss the design considerations for laterally supported beam because that is in our scope and we will design laterally supported beam only. So what are the various design considerations? What are the various aspects that we consider while designing laterally supported beam? That we will see in this part and in the next part. So first consideration is the design bending strength. How do we find out the design bending strength of beam? So this clause is, as per this clause, we can find out the design bending strength of beam, which is based on some criteria. So basically, the first criteria is M should be less than MD. Well, M is the bending moment due to the external load and MD is the design bending strength. So bending moment due to external load should be less than or equals to the design bending strength of the beam. So that is the statement that we always need to satisfy. Now, how do we find out this MD value, which is the design bending strength of the beam? So it is based on the other parameter, which is the shear force. Well, we know that if I take the example of simply supported beam, which is carrying a central point load, say W. So in that case, the bending moment value will be, say this is the L value. So in that case, bending moment will be WL by 4. And on the support, if it is centrally located, this load, if it is centrally located, then the reaction will be W by 2 and W by 2, which means they will be divided into 2. So bending moment in this beam will be maximum below the load. But because of this load, the maximum shear force will occur at the support. And that maximum shear force is generally equivalent to the support reaction. So if this shear force, so this is the shear force which we call the shear force due to the load. And if this load is factored load, then we will call it factored shear force. So now there is a criteria when factored shear force is less than or equals to 0.6 times of VD. Now what is VD? VD is design shear strength. Design shear strength of beam. So like beam has design bending strength, beam also has its design shear strength. So we will see later how do we find out design shear strength. But bending strength is dependent on the design shear strength value. So it says when the factored shear force is less than or equals to 0.6 times of VD, then how do we find out MD value? In that case, MD value will be different. If V value is greater than 0.6 times of VD, in that case, MD value will be different. So that is what IS code has mentioned. So based on IS code value recommendation, I will be showing you how do we find out MD. So here V is the factored shear force and VD is the design shear strength of the cross section. Now design bending strength MD in this case will be taken as this. So this is the same formula that is being mentioned in the IS code. So you can refer to this clause to look at it. So in this MD is equals to beta B into ZP into Fy upon gamma M naught. Now what is beta B? That we will see. This is again a factor which depends on the type of section, whether section is plastic, whether it is compact or semi-compact. So based on that, beta B value varies. ZP is the plastic section modulus. Like we have seen, My is the moment of resistance at yield strength. So in that case, the section modulus is referred as ZE into Fy. Similarly, if we find plastic moment, So in that case, it will be plastic section modulus. Okay. So at plastic moment, section modulus is different, which we refer to as plastic section modulus, and at yield strength, the section modulus will be referred to as elastic section modulus. So calculation of ZE and ZP both are different. So we will see that in later. Fy is the yield strength, gamma m naught is the partial safety factor. Now, MD can be calculated with this formula, but this value should satisfy a condition that is being mentioned in the IS code. And why we are satisfying that condition? Because to avoid the irreversible deformation. Well, load may cause some deformation to the beam under the service loading. So to avoid that deformation, this equation should satisfy a condition. Now, what is that condition? That we will see in the next slide. So it says, if we are having simply supported beam, then MD value should be less than this one. And if we have cantilever beam, in that case, MD should be less than this one. Now, ZE, as I said, elastic section modulus, and Fy is yield strength, gamma m naught is a partial safety factor. So there I have mentioned. So now the value of beta B, it is 1 for plastic and compact section, and it will be equal to ZE by ZP for semi-compact section. If the section is semi-compact, in that case, it will be the ratio of ZE by ZP. Similarly, ZP, ZE is the plastic and elastic section modulus of the cross section. And Fy is the yield stress of material, and gamma m naught is the partial safety factor. Now, that is case 1, when V is less than or equals to 0.6 times of Vd. Now, when we have a factored shear force, which is more than 0.6 times of Vd, then how do we find out bending strength? So in that case, bending strength is calculated separately, differently. So in that case, the design bending strength, which we have referred MD in the previous case, now it will be referred to as MDV. Now MDV is calculated for a different type of section. Like if our section is plastic or compact, in that case MDV will be equivalent to this value, and again this value should be less than this one in case of simply supported beam. And beta, now here is in this equation there is some new terms. MD is the same value that we have calculated in the previous case, and the new term which is being added as MFD and beta. Now how do we find out beta? Beta is calculated by using this equation, and MFD, that I will show you in the next slide. How do we find out that? Beta is dependent on factored shear force and the design shear strength of the beam. Now, how do we find out the design shear strength? Design shear strength is calculated as the product of AV into FV. Well, AV is called as shear area, and FV is the permissible shear stress. So that we will see in the next slide. So as I said, FV is the design shear stress or shear strength. AV is the shear area, and it can be calculated as D into TW and small d into TW for welded or built up section, and for rolled section it will be D into TW. Well, actually it is something like this. So if it is built up section, so in that case, if it is D, and if this is T, then AV will be D into TW for rolled section. Now for built up section, generally we make them by connecting plates using the welded connection. So in that case, this will be D, and this will be TW. So this is how we calculate this AV. I will discuss more about it, more about this AV in the slide when we will be discussing about the design shear strength in more detail. V is the factored shear force, and MD is the plastic design moment of the whole section disregarding the high shear force, as we have calculated in the previous case. And MFD is the plastic design strength of the area of cross section excluding the shear area. Now, how do we find out this MFD? MFD formulas are given. So those are, for built up section, we will use D square TW by 4 into Fy if we have built up sections. And if we have rolled sections, then in that case, MFD will be equals to D square TW by 4 into Fy. So that is the equation for the MFD. So putting all the value, we can find out the MDV value. Now, this is the case for the plastic and compact section. Now, in case of semi-compact section, how do we find out MDV value? Well, MDV value can be calculated simply by using this equation. And this is for the semi-compact section. Now, next is the design shear. How do we find out the design shear strength? So, for that, we can refer to clause 8.4 of IS 800-2007. So, as per this clause, the design shear strength, first of all, we need to satisfy a condition that factored design shear force due to the external load, it should be less than the design shear strength of the beam. So that is the condition that we have to follow, that we have to satisfy actually. Now, how do we find out this Vn? Vn is called nominal shear strength of the beam, and it can be calculated by using this one, AV into FYW. AV is again the shear area and FYW is again the permissible design shear strength. So this is AV as shear area and FYW yield strength of the web. Well, I would like to mention here that generally in I section, in the beam, we use I section, and only generally we use that only we assume that only web, this is called web, and this part is called flange, and this part is also flange. So we assume that generally the shear force is resisted by the web only. Okay, so that is why generally we use yield strength of the web, and that is why we have used here FYW, which means yield strength of the web. So sometimes in case of plate girder, we may use steel plates of different grade, but in case of rolled sections, all flange web, they will be of the same material. So in that case, FYW will be equals to Fy. Now talking about the shear area, as I discussed earlier also, this shear area, how do we find out that? Well, shear area for different section can be calculated as here. Like if we are having hot rolled section, in that case, shear area will be D into TW. So like this is the case. So in that case, you can see D is the total depth and TW is the thickness of web. Similarly, if there is a channel section, so D will be the depth of channel and TW will be the thickness of this vertical component. So that is the shear area for the hot rolled section. Similarly, if we have welded sections like here, well, they will be like this one. So there the welding will be there. Similarly, here also welding will be there. So they are being connected, they are being made by using the plates. So in that case, we will take only this D value and multiply it by the TW, which is the thickness of web. On the same line, we can say that channel section can also be formed by using the plate. So in that case, they may be they may be welded like this. Okay, so this is how we find out the shear area for the welded section. Similarly, for a hot rolled or welded section, if they are bending along the minor axis, well, in this case, bending is occurring along about this axis, which is Z axis. Okay, now if minor axis bending is occurring, like in this case, so in that case, you can see this is the Y axis, and this is actually the minor axis, and this Z axis is called the major axis. So in this case, beam will bend along Z axis, and in this case, beam will bend along the minor axis. So in that case, how do we find out the shear area? So in that case, shear area will be calculated as 2 into B into TF. Now this will be the B value, and TF is the thickness of flange. So whichever section we have, only the vertical part will be effective in resisting the shear force. So that is what we are actually trying to calculate. Similarly, if we have the rectangular hollow section, in that case, this may be a D, this may be B. In that case, A is the area of the whole rectangular section, D is the depth, and upon B plus D. So this is the relation to calculate the shear area in case we have the rectangular hollow section. Similarly, now in this case, load is parallel to the height, like load is passing through along this direction. Now, if it is parallel to the width, which means if the rectangular is in this direction and load is again vertical, and now it is parallel to the width, in that case, the shear area would be this one. Similarly, if there is circular hollow tubes, in that case, 2a by pi to a is the area of cross section of this hollow circular section, and with this we can find out the shear area. Similarly, if there is plates, solid bars, then we simply need to find out the area of those plates, and area of those plates can be calculated. Like in this case, a plate is having T thickness, and say this is the width, so B into T will be A. Okay, so this is how we find out the shear area for different sections. So when we multiply this shear area with the yield strength or permissible shear strength, then we can find out the design shear strength of that particular section. Now, next criteria is maximum deflection. Well, maximum deflection is again need to be checked as per IS code using the table 6 of IS code. So we will see in more detail when we will be solving the numerical in the next lecture. So basically, why do we check for maximum deflection? There is some criteria, like a beam is designed to have adequate strength may become unsuitable if it deflects excessively under the load. Well, a beam may support the required load, but if it is deflecting more, in that case, the functioning of the beam may become unsuitable, and in that case, what we can do is we have to restrict the deflection. So that is why we are supposed to check the maximum deflection criteria as per table 6. So as I said, beams that deflect too much may not normally lead to the structural failure, but nevertheless endanger the functioning of the structure. As I said, beam may take the required load, but at the same time, if it is deflecting more, then they may endanger the functioning of the structure. Like if this is the beam, if it is carrying the load, and because of this load, if it is deflecting like this is the deflection. So if this deflection is higher, in that case, we may feel, or any occupant may feel uncomfortable. So in that case, the functioning of the beam or the structure will be endangered. So That is why the deflection in the beam is restricted by the code of practice by specifying deflection limitation, which are usually in terms of deflection to span ratio. So we will look in this in more detail when we will be solving the numerical. Now, how do we find out the actual deflection? Basically, to check the deflection limit, what we do is there is a limit which is given in the IS code. So we generally what we do is the beam to be safe in maximum in the deflection criteria, the actual deflection in the beam should be less than the permissible deflection as per IS code. So basically, we say actual deflection should be less than or equals to the permissible deflection. Now, so this permissive deflection, we can find out this limit from the IS code, but how do we find out this actual deflection? Well, this actual deflection depends on many various things like the support condition of the beam, what kind of beam is there, and the type of load beam is supporting. So that is the factor that generally depends. So here I have shown some example like this is the first case when there is a simply supported beam which is carrying a central point load, and in that case support reaction will be W by 2, and in that case a bending moment will be WL by 4. So this is basically the bending moment, and in that case how do we find out deflection? So this is the formula for deflection. So in this case deflection would be WLQ by 48 EI. Now W is the load, L is the effective span, E is the Young's modulus of elasticity, I is the moment of inertia of the beam section. Similarly, if the beam is carrying UDL over the whole span, so in that case bending moment will be WL by 8, and maximum deflection can be calculated by using this formula, which is 5 WL by 384 EI. So this is the formula to calculate the deflection. Similarly, if the point load is not at the center but at any other place in the beam, in that case bending moment will be WAB by L, and deflection formula will be this one. Now A is the distance from this support and B is the distance of load from this right support. Similarly, if the UDL is not over the whole span but some part of the span, like this fourth case, in that case bending moment can be calculated by using this formula, maximum bending moment. So I'm writing here, this is actually the maximum bending moment. So maximum bending moment can be calculated by using this formula, and the maximum deflection can be calculated using this relation. Similarly, there may be some other case also, like if there is UDL and varying load, in that case this will be the maximum bending moment and this will be the deflection, maximum deflection formula. Similarly, if there is again a case of varying load, this is again a case of varying load, but I mean the intensity of load is different and the variation is different. So in that case maximum bending moment can be calculated using these relations, and maximum actual deflection can be calculated using these formulas. So once we find out the actual deflection, then we will compare the permissible deflection, and then we will see whether our beam is safe in deflection or not. So we have to ultimately satisfy this condition. So we will continue our discussion in the next part. Thank you.